Welcome to the 5-3 practice set. This is the first problem assigned. A car at the Indianapolis 500 accelerates uniformly from the pit area, going from rest to 270 kilometers per hour in a semicircular arc with a radius of 220 meters. Determine the tangential and the radial acceleration of the car when it is halfway through the arc. Assuming constant tangential acceleration, if the curve were flat, what coefficient of static friction would be necessary between the tires and the road to provide this acceleration with no slipping or skidding? Okay, so we have an unbanked road. All right, so that means eventually we're going to set our centripetal acceleration or our centripetal force equal to our friction force. But before that, we need to find out what our centripetal acceleration and centripetal force are going to be, understanding that this is non-uniform circular motion. So there is going to also be some tangential force. Now, luckily, tangential force and tangential acceleration work just like normal one-dimensional kinematics. So the fact that it says that we can assume constant acceleration in the tangential direction means that we can probably use one-dimensional kinematics and the information that's given in order to find that tangential acceleration. All right, so what are we given? Looks like we're given an initial velocity of 0, so I'm going to go ahead and write down given. We have an initial velocity of 0 meters per second. We have a final velocity, or we don't have a final velocity. Yeah, we do. We have a final velocity right here. So that's 270 times 5 over 18. So that's V final. 270 times 5 over 18, which is equal to 75 meters per second. Now that 5 over 18, if you don't recall, is just the conversion factor to go from kilometers per hour to meters per second. Now, this is a semicircular arc. So one thing to remember about semicircular arcs is that a semicircle is generally assumed to be half of a circle. So that's actually really useful to know, because if we can find the circumference of a circle, we could find the distance of a semicircular arc just by dividing that circumference by 2. So then we have our delta x, our distance. Oops. Delta x, let me get the blue. Delta x is going to be equal to, well, it's going to be equal to, instead of 2 pi r, it's just going to be equal to pi r because it's half of the circumference. All right, and if I go ahead and plug in the 220 radius, the 220 meter radius, and then multiply that by pi, then I should get something like, let's see. Yeah, 691.15 meters. All right, so that's our delta x here. And if we're looking for the tangential acceleration, then I'm going to pick one of the kinematic equations that takes what I have and is going to spit out acceleration, or it allows me to solve for acceleration. The first one that comes to mind is, I believe, Vf squared is equal to V naught squared plus 2a delta x. All right, plugging in what I know here and then solving for acceleration is just a couple of steps. I'm going to plug in that 75 meters per second over here. That's going to be squared. The initial velocity is 0, so I can cut that out. And then it's going to be 2a, and then for delta x, I'm going to plug in 691.15 meters. Good. Now, in the calculator, I'm going to go ahead and square 75. And then I'm going to divide it by 2, and then I'm going to divide it again by my delta x, 691.15. And that gives me about an acceleration of 4.1, taking that to 2 sig figs because my 75. All right, so if I have an acceleration of 4.1, and remember the units, that's going to be meters per second squared, then I can say that that is my tangential acceleration. All right, so knowing the tangential acceleration is a very important step, because now that I know the acceleration, I can find the velocity at any point on the path. Using kinematics still, I can find the velocity at any point on this semicircular path. All right, so let me move this a little bit over. Actually, let me not take that. Let me move this all a little bit over. All right, I'm going to do a little bit more math here to the right. I'm going to go ahead and use the same kinematic equation. I'm going to say that V final, and I don't know what V final is yet. V final squared is equal to, V initial is still going to be 0, so this is going to be equal to 2 times 4.1 meters per second squared times delta x. And in this case, delta x is going to be not the full semicircle, but half of the semicircle. And I'll explain why in a second. So instead of the 220 times pi. I'm going to do 110 times pi. All right, so as you can see, we have everything here except for v final, and this is going to help us solve for v final. But why the 110 pi? Well, if we come back to the question, it says, we need the radial acceleration here. I see it right here. So we need the radial acceleration of the car when it is halfway through the arc. So halfway through the arc is literally at the quarter point of the whole circle. All right, so now instead of just dividing 2 pi r by 2, we're going to divide 2 pi r by 4, and that's essentially going to give us 110 pi. So now we're talking about a new distance. And the reason why we need the velocity at that point is because you know that centripetal acceleration is found using velocity and radius. So as soon as we know the velocity at that point that it's asking for, this halfway point in the arc, then we can find centripetal acceleration. When we have centripetal acceleration and tangential acceleration, we're almost done with the problem. So let's go ahead and find that velocity at this middle point in the arc. All right, so I'm going to multiply 110 by pi. Then I'm going to multiply that by 2, and I'm going to multiply it by 4.1. So that's combining everything on my right side. So that means v final squared is going to be equal to 2,833.7. Now, if I go ahead and take the square root of that, I'm left with about 53. And that's going to be meters per second. Let's keep one extra significant figure here just for good calculation. All right, great. So now we know exactly what the velocity is, the tangential velocity or linear velocity at this point. That velocity is going to be equal to 53.2 meters per second. We want to know finally now what the force is and what the acceleration is pointing towards the center of that circular motion. All right, so keep that in mind. We're going to go ahead and get rid of some of this information right here. We're done with the kinematics. Now, we can find the centripetal acceleration very quickly now because we know that that's going to be equal to v squared over r. And we have v and we have r. So I'm going to go ahead and then square my v. And I'm going to divide it by the 220 meter radius. That should give me about 12.88. And that's going to be meters per second squared. All right, so back to the question. It says determine the tangential and radial acceleration of the car. We've done that, okay? When it's halfway through the arc. All right, so the tangential acceleration is constant all the way through, so it's the same at any point, but the centripetal acceleration is going to be different at each point because the tangential velocity is increasing. So at the halfway point of the arc, we have a centripetal acceleration of 12.88. Now, it says if the curve were flat, what coefficient of static friction would be necessary between the tires and the road to provide this acceleration with no slipping? All right, so now we just really have to consider the centripetal force, and we're going to set it equal to the static friction force to see how much static friction we're going to need. So we know that the friction force is just going to be equal to our m times the mass of the car times 12.88 meters per second squared. All right, so that's Newton's second law, F equals ma. And we're going to go ahead and take that and we're going to set it equal. So I'm going to take that mass times 12.88 meters per second squared. And I'm going to set that equal to my formula or my expression for finding the static friction. That's going to be mu sub s. All right, guys, this is the coefficient of static friction, mu sub s, times mass times gravity. All right, and that mass times gravity is the normal force. You guys should know by now that the expression for static friction is mu sub s times normal force. Mg represents normal force. I wrote it as mg so I can go ahead and cancel out the mass here. I don't want any of that. And then really quickly here, I can go ahead and solve for mu sub s by dividing both sides by g. So that's going to be 12.88 meters per second squared divided by 9.8 meters per second squared. All right, so if I go ahead and divide that by 9.8, I'm going to get a mu sub s of about 1.3, which is a pretty insane static friction force. But there you have it, guys. We have found every bit of this non-uniform circular motion problem, all the way down to how much static friction we would need in between the road and the car in order for it not to skid, even though it's going so fast. All right, guys, I'll see you in the next one. Here we are with problem 2 in our 5-3 practice set. It says, for each of the cases described below, sketch and label the total acceleration vector, the radial acceleration vector, and the tangential acceleration vector. For A, a car is accelerating from 55 kilometers to 70 kilometers per hour as it rounds a curve of constant radius. Now, if the tangential velocity is changing, then you know there must be tangential acceleration, obviously, right? So let's assume that for all of these instances, we're going to start on the right edge of our circular motion. Now for part A, we know if we are moving in a counterclockwise direction, then we know that we must have some tangential acceleration going up right here. And the reason why I say that is because we are accelerating into our curve. So if, again, as I said, if this value is changing, if the linear velocity is changing, then we do have a tangential acceleration and tangential force vector here. So I'm going to say that this is A sub tan for tangential. All right, there's going to be some tangential acceleration vector here. Now, of course, there is going to be, if it is moving in circular motion, there is going to also be some centripetal. And this problem says radial, but radial is actually just another word interchangeable for centripetal. And that's kind of where that capital R subscript comes from for this force vector as well. So we can say that there is definitely an acceleration sub R here pointing in this direction. And then there's going to be the resultant vector, or the total acceleration vector, that is going to be pointing somewhere in between these two vectors, and it's going to have a greater magnitude than the two. We're going to say that this is just the acceleration vector right here. All right, so this should look something like this, where you can kind of put together a box here if you want it to be drawn to scale properly. All right, now let's go ahead and look at number 2. It says a car is going at a constant 65 kilometers per hour as it rounds a curve of constant radius. All right, so we have constant radius and we have constant velocity. That means this is uniform circular motion. There shouldn't be a vector that represents tangential acceleration because we have constant velocity, so the acceleration is 0. So that means in this case, the total acceleration is all centripetal. It's just all going to be pointing towards the center of the circle. All right, so A total is just equal to A centripetal here. That's all there is to it. And that's whether it was going this way or this way, so no worries there. But for all of these, let's keep the same convention that we're going counterclockwise. All right, at C, a car slows down while rounding a curve of constant radius. Okay, so one more time, if we're moving counterclockwise but the car is slowing down, then that means there must be some negative acceleration. So we're going to say that at this point, that's going to be an acceleration, a tangential acceleration pointing down. And then still, because it's in circular motion, there's still going to be a centripetal acceleration pointing towards the center of the circle. So this is going to be A sub R. Don't forget your vector notation signs up here. And then if we were to make a box here, then we can say the resultant vector goes to about here. And this is just going to be A. Now, these are the correct or these are representations of what could be the correct acceleration vectors. Remember that the force vectors may have different magnitudes, but they will be pointing in the same direction as well. And that's all there is to it for this one. Hopefully that helps you understand how vectors are drawn, how to get the resultant from them, and everything else. I'll see you in the next one. Vector. This is the third problem in our 5-3 practice set. A particle revolves in a horizontal circle of radius 1.95 meters at a particular instant. Its acceleration is 1.05 meters per second squared in a direction that makes an angle of 25 degrees to its direction of motion. That's 25 degrees to the tangent line. Determine its speed at this moment and 2 seconds later, assuming constant tangential acceleration. All right, so first off, it'd be good to go ahead and sketch this diagram out, or let's actually make that a circle. All right, and I'm going to go ahead and take the spot that I usually take and assume that this is starting at the right-hand point. All right, we know that there's going to be some tangential acceleration, And the reason we know that is because the total or resultant acceleration direction is not directly towards the center. So we know there's going to be some tangential acceleration, and that we know that there's also some centripetal acceleration. So I'm going to go ahead and draw out my vectors here. Problem 2 was meant to kind of prep you for this step right here. And then, so we're going to say that there is the resultant acceleration, or the total acceleration, you might say. And this is the one that's going to be equal to 1.05 meters per second squared. All right. And it's going to have the components of the tangential and the centripetal acceleration. All right. So if this angle right here is 25 degrees, 25 degrees, then we can really quickly find the centripetal acceleration and the tangential acceleration using a little bit of trigonometry. So really quickly off to the side, if I could say that a tan, the tangential acceleration should be equal to, considering that this is adjacent to the angle, this tangential force acceleration vector is adjacent to the angle, I'm going to say that it's 1.05 cosine, 1.05 cosine of 25 degrees. All right, and then for the centripetal acceleration, that's just going to be 1.05 sine of 25 degrees. We're going to use both of these for this problem for the two different velocities that it's asking for, the two different speeds it's asking for. So let me go ahead and calculate them really quick. 1.05 cosine 25 should give me about 0.95, and then 1.05 sine 25 should give me about 0.44. All right, so that means I can go ahead and label 0.44 meters per second squared, and then right here 0.95 meters per second squared. And that way it's a little bit messy, but you can see that my diagram is labeled. And the question is asking determine its speed right now. That's part A, determine its speed at this moment. Well, now that we know our centripetal acceleration, we can say that A sub r, we can recall that A sub r is equal to v squared over r. And we are given the radius, so we do have enough information to find the velocity at this moment. Let me go ahead and plug in my 0.44 meters per second squared is equal to v squared over 1.95 meters, 1.95 meters. All right, multiply that 0.44 by 1.95. We should get something like 0.865. That's more sig figs than you would normally need, but we're just going with it for a good calculation, is equal to v squared. All right, so if I go ahead and take the square root of that 0.865, I should get 0.93 is equal to v. So that's 0.93 meters per second. All right, so this would have been meters squared per second squared if we're trying to keep up with our units. But this is going to be the velocity right now, and that's going to be pretty important for us to find the velocity 2 seconds later. Because what we're going to do is we're going to just consider our tangential acceleration. All right, let me move this down over here. We're just going to consider our tangential acceleration, and we're going to use some kinematics because, as I've said in a previous problem from the set, when you're just talking about tangential acceleration, we can pretend like it's one-dimensional kinematics, assuming that we have constant acceleration. And luckily, it tells us straight away we can assume constant acceleration for part B. Fantastic. That said, let's think of a kinematic equation that would allow us to find the velocity if we have the initial velocity and we have the acceleration and time. That's going to be, let's go to blue here, v sub final is equal to v initial plus a t. We have v initial, we have a, and we have t. So I'm going to go ahead and say that v final after 2 seconds is going to be equal to my 0.93 meters per second plus my acceleration, the tangential acceleration, because that's the part that we can treat like one-dimensional kinematics, is 0.95 meters per second squared. And I'm going to multiply that by 2 seconds. All right, so that's 2 seconds. If I go ahead and plug that all into the calculator, I can say that the 0.93 plus 0.95 times 2 gives me a final velocity of 2.83 meters per second. So given the information that we have, we can say that at the point where the centripetal acceleration is 0.44 meters per second squared, then the velocity is 0.93 meters per second. But at the point 2 seconds later, we can say that the velocity is 2.83 meters per second. I really like this problem because it forces us to really draw the diagram, do a little bit of that trigonometry that we need to still be good at, and then solve for all of the components. All right, guys, good luck, and I'll see you in the next one.